normally when the I2C is going to be implemented, what we do, we use a electronically erasable programmable ROM. Okay, so we want to use EEPROM, right? This will be used for implementation of the I2C using any microcontroller. Okay, so I want to implement using I'll say maybe this is example 8051. So most of the time for uh, graduation level we stick to up to 8051, and 8051 will be the most complex one. Okay, so out of whatever they can ask, I think even our question papers we can refer and we can identify that. Okay, right, up to 8051 itself it has been asked. They can ask the coding in terms of assembly level language or the C program. Okay, but again, when it comes to the actual implementation part, people prefer writing it in the embedded C or generally C. Okay, maybe when you go to the industry, you'll use the slightly different version called of C called embedded C. Okay, right. So right now we are not going to do that. We'll simply implement the concepts of I2C using C program. Okay, but when the again slightly modified versions of I2C are available, right? But whenever you are trying to implement using the I2C using a microcontroller and a EEPROM, this particular, there is a slightly different name. It is ultimately the base version of I2C still remains same. Okay, but when we try to implement this, it's called as the I2C bus protocol. Okay, so that's the name we use here. Okay, so one such EEPROM is like this. So directly we'll look at the basic structure and basic features of a EEPROM, right, which we are going to use. The same thing is there in our question papers as well. Okay, so there is a 8-pin EEPROM, right? So 1, 2, 3, 4, 5, 6, 7, 8. Normally they will ask, right, the connection. According to that we just have to write, that's all. So this is one, two. So it's a 8-pin dip package. All right, so this is called A0, A1, A2. It's a ground. Then the power supply will go to the VCC. This is right, SCL and SDA. So these are the various pins available on this. So fine. This is the EEPROM which we are going to use. Okay, right. Now, what are the fundamental features, right? What are the basic features of this? First, we'll see that, right? Then we'll look at the control bytes. What are the, how do you control them? Because you want to write something, you want to read something. So the I2C protocol is basically used for the reading and writing the data, right, between the controller and some memory location. Now in this case it is a EEPROM. Okay, right, now we want to do a read and write operation. It's not a simple read write, you have to follow the protocol that, right, some certain rules. That's why it falls under the category of a protocol. Okay, right. Now okay, let's look at the fundamental characteristics of the EEPROM. All right, so this is basically, all right, there inside you have 8 blocks of memory, right, and you have each block is of 8 it's k, okay, it's kilo bit, right? So totally 8 into 8k, so totally you have 64 kilo bits. All right, so that's the measurement, that's the size. Now in order to read and write this EEPROM, right, I have to use the I2C, right? So the interface will be right, interface will be two wire system, right? Because I2C uses two wires basically. So using only two wires, I can read and I can write. Okay, it depends upon what type of signals you send and when you send. Right, the protocol says that okay, you have to make this high at this time, make this low at this time. We'll come to that. Okay, I'll come to the protocol later. Right now, I'm looking at the hardware part. Okay, then whenever you want to write something, there is a page write buffer which can take up to 32 bytes total. Okay, so there is a write buffer, right, up to the 32, right? So we can read, write, right, normally whenever the EEPROM is manufactured, you see that it is programmable, it is erasable, and you erase electronically. So which means I can write something, erase, once again write, then erase, once again write. It's possible. So when it is manufactured, again, the one, I'll give a name here. I think the same one, it's the same structure. It doesn't matter who will manufacture. So the one which I'm considering as a reference is called as 24LC64, right? This is a basic EEPROM. The manufacturer is Microchip. Okay, many other versions. TI will also produce the same thing, but their name is different. But anyway, ultimately, when I refer the question paper, I can see that the pin diagram still remains same. Okay, you have the same pins, right? So it doesn't matter who will manufacture that, right? Just use that number over here when you write an answer, say in an exam. All right, you just say that okay, the EEPROM number is that, whichever they ask in the question. Okay, doesn't matter. It's the 8-bit representation, 8-pin package. What they use will definitely look like the same. Okay, all right. So these are the fundamental features. The microchip says that you can read and write 1 million times. Right, the lifespan of this read write is 1 million times. 1 million times you can read and write once again. So until then, nothing will happen. Something like whenever they give a switch, they'll give a lifetime life cycle, right? So like so many hits of the switch, it will not break, right? So something like that. It's the same. All right. So this represent something like that. Now we'll move on to the control. How do you control? Because when I want to say I'm writing, I'm reading, right? I have to have a control register. All right. So this is the control register structure. Okay, now, okay, let me write the control structure first, then we'll discuss. Okay, so basically, initially it start with the start bit. All right, then we have 4 bits of the control code that needs to be inserted, right? That's after the start. Then we have 3 more bits of the chip select, right? Because you may interface, say, multiple EPROMs, right? Exactly which EPROM I have to write or read, I need to understand. So for which we have this. Then I have another bit that is for read and write bit. Then I have a acknowledgement bit. So this is the total, right? You can see that 1, 2, 3, 4, 5, 5 plus 5, totally 10 bits are there in the control register. So let me write what we are trying to do. So the 4 bits what we have here, it's the control code, right? Then the upcoming 3 bits are used for the chip. So now you see we have 3 bits for chip selection. How many chips you can actually interface? 2 to the power 3, right? So eight I can use because every chip can have unique address. So starting from 000 till 11. So that actually is 8, correct? So that till there we can have it, right? So that's the meaning. Then we have there is what is called as a R/W bar, right? So this is a read or write. Then this is ACK, stands for acknowledgement. All right, so these are the various this thing. Now, out of which here we have a 7 bits all together called as the slave. Okay, this is the slave's address. So slave's address contains two things. First is a control code saying that whether you are going to what kind of operation you are performing. Data transfer, read, write actually has 1010, right? Whenever you see 1010 here, it understands that okay, now the operation that's going to be performed here will be a read or write, right? Then this bit will decide whether you are reading or not. Okay, right, so it will always remain 1010 in our case. Okay, it will not it's not going to change because right now our intention is you can even see the questions in our question paper which just specify that, right? Tell how do you read from a memory, right? How do you read write to a memory? These are the kind of questions, so definitely this is not going to change. All right, so now let's look at the I2C, right? So I need to know about the I2C protocol, right? Now, fine. Let's look at the I2C protocol. Then we'll proceed to the interfacing. Okay, right. So I2C, as we know, it uses what is called as a two-wire system. Okay, so let me write the I2C structure here. Okay, so the I'll I'll talk about I2C. Okay, now it's a communication protocol. Uh, you have something called as, so it's called as a bus interface system. I'll just write BIS. Okay, so in short, it is a bus interface system. This particular system is consisting of the buses, and buses in the sense you understand the word bus, right? Yeah, it's a set of wires responsible for carrying the data, address, and the control signals from device to device, right? In the device to device communication system, right? Okay, it can have two or multiple wires or 10 wires, 100 wires, doesn't matter. So this BIS basically is the it represents the all the buses present in your system. Okay, right. So it's actually I'm writing it in the block diagram system. Basically, it's not that, it's simply some wires. Okay, so I'll take few wires from this, saying that okay, bus interface system has many wires, out of which I'm taking out one wire. All right, okay, again I need a power supply line, so I'm taking a third wire, right? Let's say this is the VDD VCC whatever, right? So power supply comes from there. Then if you look at our block diagram or the EEPROM, we have two uh, connections. So two pins named SCL and SDA, they are responsible for a clock and the data, right? Represent data. You carry the data using them. So you see here, this is SDA, okay, and this is SCL. Right now we are just talking about the I2C. That's why I'm taking only three wires I require. Okay, fundamentally only two wires, SDA and SCL, but I need to show that okay, I need a power supply. Okay, that's why I have taken the VDD as well. Now you see, in the whole system you are going to use a master who is the controller of the data transfer, or whatever operations has to be performed will be controlled by a master. Okay, so in our case, who is the master? 8051 microcontroller will be the master, because you are writing a code to instruct the microcontroller what to be done, what has to be done, right? So I'm saying that okay, when first part of the code runs, it will initialize something. Next part, it will do the read operation. Next, it will do the write operation, right? So right, etc. You see, you are writing the function, you are writing your program, C program to the master. So right, so that who will do the required. Then right, other than that, you can have not just one, you can have multiple slaves. So the EEPROM, what we are connecting to this system is a slave. Okay. So our intention here is that I want the master, in the sense, the microcontroller will send some data to slave. That's a write operation. How to do that? We want to check. Okay. Then master wants to read some data which is already present in the slave, a particular address. Okay. Master sends an address, slave has to put that data on the data line so that master can read it. That's all, right? The operation is very simple. So we just have to stick to the protocol. That's all. Okay. All right. So I'll just show few connections over here like this. You can have one connection with the data line, one with the clock line. Okay. So you have multiple slaves. So this is slave one, slave two. I can have slave n, right? Again, here we are in this diagram. I'm not writing any specific microcontroller or any specific slave, right? This can happen, right? You can have any number of slaves depending on the capability of the master. Is it okay? Then always between, I wanted to show this because later on when I make a connection, it should not confuse. Okay, so there will be a resistor. It's a pull-up resistor. Okay, that actually pulls up the, whenever the voltage is high, right? It will pull up the value on that line to a higher value. Okay, so you can have a RP, R pull. Okay, that resistor will be there. Okay, SDA, SCL are the two lines used for communication in this particular protocol. Okay, only two wires. Okay, right. Fine. So first thing to remember is only two lines. Okay, any number of device you connect, right? The data transfer happens only through two lines, right? It's not just data transfer, it's also the control, right? Because when to write, whom to write, which device should send the data on the data line, etc. Many things are there, right? So normally if I look at the computer architecture, we need three types of lines, right? One, data lines, maybe depends on the size of your data. If it is eight bits, you need eight lines. If it is, say, whatever 16 bits, you need actually 16 lines to for parallel data transfer, right? Okay, fine. Now let me write 2 points over here, which will be helpful. So the first point is just two wires. This is actually a advantage of I2C over all other protocols, many of the other protocols. Okay, so the data will be sent or received by using what is called as SDA, serial data. Okay, and you need to use, see, there has to be a synchronization between master and any of the slave, either you are writing or reading, correct? In the sense, I'm saying right now I'm sending, the slave should pick up the signal which is coming from the master to the slave at the same very same moment. There should not be a delay, right? So that is called as the synchronization. For synchronization we use the clock system, clock based system, right? Clock signal. So that is SCL. So SCL stands for that. Okay. Right. Now, out of all the communication protocol, there are three major types. If you remember, right, you have a right, one directional, there is a half duplex and a full duplex, right? So out of which this I2C falls under a category called half duplex. Why it is half duplex? Can you tell me? What is the difference between half duplex and the full duplex? Our mobile phone, is it half duplex or full duplex? Because both of them can talk simultaneously and hear simultaneously. When I talk, even if you talk, no problem. I'm able to hear what you are talking. At the simultaneously, you are also able to hear what I'm talking, right? That is full duplex. Both of them can transmit, receive simultaneously. That's right. Half duplex is one person can talk at a time. Like a best example, walkie talkie, right? So you press the button, you talk, right? You release a button, other person talks, right? So that's the technique here. So that's a half a duplex system, right? uh by it, so I'll write like this. So uses the bidirectional uh, buses makes more sense, right? So all the buses what we see here are bidirectional. It can actually, if I go back and show, right, it can carry the signal left to right as well as right to left. Okay, both are possible, that's why it is bidirectional. But since I have limited number of wires, right, simultaneously both should not be able to, right, both should not send, correct, that's all. Right, you use only one line for data transfer, right, which means only one can send a data at a time, right, uses bidirectional buses, but only, yeah, one device can send data at a given point of time. That's the fundamental thing. So normally master will decide who is going to send. Okay, so that's about the data lines. SDA will carry this data, whoever is going to send. Okay, now the clock is used to control the data transfer and the synchronization, right? So who is the control signal here? Anyway, we don't have to go for a very complicated control signal generator, or there is no separate circuit to generate the control signal, right? If you remember the basic architecture of any of the microprocessor, microcontroller you have studied, there is a control unit, correct? Internally, you will see in addition to our whatever, whichever device, which is the ALU, fundamentally that's the one who does all the addition, subtraction, right, etc. Addition to that, you need to have a control unit who is responsible for generating the control signals of for each and every other blocks present inside that. You may have a ADC, DAC, right? Look at the various blocks present over there. Every block you need to generate the control signal saying that yes, now you do the write signal. Yes, now you do the read. Yes, now you add, right? Now you put your result onto this bus so that it goes to this address, like that. You see, so many things are there. So that's actually you need to have a complete block for generating the control. But here again, I2C is pretty famous because of this also being one of the very strong feature, right? So there is a clock bus, right? That is SCL. What is the fundamental feature? It is used to control and, right, I'll just write, controls the data transfer. It controls the data transfer and the synchronization. Okay, so it's understood by now that there is only one clock, and all the devices that uh, every device that gets connected to this I2C bus, in the sense these two lines, right, will share the same clock signal. Okay, fine. So later on, when if at all we go to any higher level problem, you will see that the normally the master is the one who is responsible for generating the clock signal. Okay, but at times we have the situations wherein the master can give this controlling of the clocks, that facility, right, can be given to the slave as well. Okay, it's possible, but mostly we will not see such examples in our case, right, because our intention just to look at the I2C and write fundamental programs. Okay, right, now okay, let me just check it out. All right, let's go to the working of this. All right. So before this, we actually have many topics, but I think that is not necessary, because when I look at your questions and all, I understand that okay, they are not going to ask that part, right? Like what are the physical layer architecture, etc. I think that's not there, right? Physical layer. Have you studied physical layer somewhere else? Maybe you have come across like network architecture or networking. Some Okay. Protocols. When you study the protocols, you might have studied that. Okay. Right. Okay. Okay. Right. So that is applicable even for this protocol because it is a protocol, right? Right. But right as of now, I'll not go to the physical layer of this protocol. All right. Okay. Now, so fundamentally, we understood so far that I have one chip which is a microcontroller. There is another chip which can be EEPROM, ADC, DAC, whatever. I want to communicate between them, right? So whenever the master wants to, who is the one to decide? Master. So master wants to communicate with the slave, right? So this is the first step. So the master uh, asserts the start bit. So that is denoted as S in our architecture. If you in our control register, you can see that. Okay, I didn't write, so I'll just write this S is the start start. Okay, so now I am talking about the S. So whenever master wants to start, master asserts the start bit S. Okay, followed by the address of the slave. Again, this is possible when you have multiple slaves connected, right? With the whether you want to read or write, because it has to be decided by the master. Master wants to read means master makes the read write bit as read, right? Otherwise it will be in the write option. Okay, read or write bit. This is the step number one. Whenever master wants to do an operation read write, it is the first step, right? Now after asserting the start bit, all the slaves will be, right, very attentive. It's like you are activating all the slaves using this. Okay, when S is 1, everybody will be alerted saying that okay, now some communication is going to happen. But slaves, maybe there are 4 slaves connected and nobody knows to whom the master is going to address now, right? That address will come in the form of a slave address, right? So you can see that in the control code we have the chip selection. They are the addresses, right, to which you want to. So again I can write it as A2, A1, A0. So you can see that A2, A1, A1, A0 were there in our right, in the EEPROM as well, right? So you can see A2, A1, A0. That's all. That's what. Okay, fine. Now, fine. So next point I'm going to write in this way. This is the next step in the I2C protocol, right? So all slaves uh, they get attentive, and if the address if the address matches their own address, okay, then that slave, only one slave, okay, then that slave sends the ACK acknowledgement saying that yes, I am here, right? So sends the acknowledgement ACK bit to the master. So step number one. Now, once the acknowledgement bit is received, the master will start the communication. Okay, let us assume there are two possibilities. One, there is a acknowledgement received. If the other case is there is no slave whose address matches to the transmitted address, right? then it is considered as a NACK, no acknowledgement. This thing. Okay, so what happens? The in such case, master asserts the stop bit to stop the communication, because there is some confusion. The address which I sent is not existing, so I want to stop the communication for the given at the given moment. Right? I will reinitiate it later after checking the address of the proper address. Right? That's what is the meaning. Right. So I have two more points here. So if the ACK is received, this means the master starts communication. If no ACK, that means acknowledgement is not received. So that means the master asserts stop bit to stop the communication. Is it okay? Fine. Now we have to look at the form in which the data gets uh, uh, transmitted between the uh, in on I2C. Between any of them, maybe master to slave or slave to master, doesn't matter. Okay. Now, basically, the I2C, I'll just write the, maybe this is like the data frame. So initially, first what you saw was a control frame, control byte, right? That is sent first, right? That says that start of communication, followed by, you will specify the 7-bit address which contains read or write, followed by the 3-bit address of the particular device. That's the uh, that corresponds to the operation you want to perform, plus the 3-bit address. Okay, A2, A1, A0, right? So followed by that, you have read or write byte, write bit, saying that whether you want to read or write, right? And after that, you have the acknowledgement or no acknowledgement. Normally, acknowledgement means yes, the device is present. No acknowledgement comes means it normally remains zero. So that means there is no such device on connected on to this I2C bus. So that's the control. Now we'll look at the data frame. So the data frame will actually contains our control followed by the data frame. Okay, so first I'll simply write the control byte. So you understand what is a control byte. This can go, it's what it includes. It includes the start, the one which we draw already, right? This is that one. Okay, just see this whole thing, right? How many bits are there? 10 bits, correct? All the 10 bits corresponds to the control register or control, I'll write control byte. Okay, so that this whole thing is a control byte which I have written here. Okay, this is a control byte. Followed by this, you keep sending the data in a specified manner. That is, you may have 8 bits, 16 bits, 32 bits, 64 bit, depending on your architecture, you can send. But now we are restricting it to the 8051. So 8051 is 8 bits. So I'll write only 8 bits. Every data is 8 bits. Every data is followed by either acknowledgement or NACK. Okay, if not received, you get a NACK. Okay, but I don't write that. I'll just write the ACK. Once again, 8 bits. Next 8 bits of data, and so on. This will continue. But at the end, when you want to stop, right, it will be like this. Okay, let me slightly reduce its size so that I can accommodate everything. Okay, let's assume that we had two sets of 8 bits. 8 bits are over. You have to get a acknowledgement. Once your data set is completely sent, whatever data you wanted to send, let's assume it's complete. So you have to send a stop. Okay. So this is the protocol. This 8 bits acknowledgement followed by 8 again acknowledgement. This can repeat any number of times as you want. Is it okay? Right. Now, what do you mean by start? Because initially we understood that there is a start and there is a stop, correct? So two things have to be identified first. So I'll write the start condition. So start condition is basically represented in the form of the combination of SDA and SCL. So if I say this is the SDA and this is the SCL, high to low transition of SDA while the SCL is high. I'll write the sentence, but before that, let me show you. Right? This is how it happens. You see, there is a high to low transmission transition happening on SDA. Okay, while the SCL is high. Right? So this particular condition is called as the start. So I'll write the condition here. The condition is very simple. A high to low transition. High to low transition of SDA. I can see that. Yes, SDA is high initially, it becomes low. But that's not the only required condition. I have another required condition. That is while the SCL is, it should be high. It should not be low. When SCL is low, if the transition happens, that doesn't mean anything. Is it okay? So this particular condition itself is called as the starting condition, right? The whenever the master does this, right, does this operation, all the devices will be activated, saying that okay, some communication is going to happen now. So that's the indication. Okay, that's the starting condition. Similarly, I have a stop condition. So stop condition is also very similar, right? I have SDA here. SDA will be initially low and it will become high, right? Whereas the SCL will be high already. So this particular condition, if you can see on the lines SDA and SCL, then this will be the indication of the stopping of the communication, which is already happening. Right? So who is responsible for this? Right? Master is responsible for this. Okay. Now I'll write the condition a low to high. Okay, low to high transition is required on SDA when, what is the condition? SCL is high. So that is the condition of this. Are you okay? Right. Now let's move ahead to the address frame. Do you have the address frame, etc., in your syllabus? Just for your, I just want to know that. Yeah, correct. So in the I2C address field, right? Normally you have okay, I'll just go back to show you what I'm talking about. I think it's already done, but I just want to know whether they have done it in more detail or what we discussed so far. That's all you see here, right? See, this is the address I'm talking about. These fields. Okay, so that actually has, right, on this side I call it as a MSB, right? This side is the LSB of the address, right? So here, right, normally, right, we will be trying to send, right, initially when I send initially, I try to send this as the control register, okay, control byte. Later on I'll be sending the message what I want to write, that's all. Okay, so that's the only thing. There is other than that there is nothing much. So okay, so what we are sending, anyway, I'm going to show you that in detail when we write the program. Is it okay? All right, so let me check what else we can write. Okay, already we have done that. Okay, so I think this is what is enough for us to look continue with what is our basic basic question was, right? So I want to look at the program using which I want to write. I want to write the programs for doing the operations, such as I want to read initially, then I want to write, and maybe I want to write see the okay, first let's write the fundamental what you call equations and the code for reading and writing. Okay, so let's do that first. So anyway, we have written the start and stop condition here, right? What I do, I'll make some space, and okay, no problem. Let me, I don't have a space. I'll write here. So let me divide this. So on this side, I'll write the code for the start condition, right? So you see, the questions can be formed in any way, right? So I'll give part by part so that you can club all together to get the required answer. Okay, I'll tell you that. So, but let's look at the start condition. Okay, so the start condition is like, right? I have nothing to return, so this is void. Okay, start I2C is my function. And are you passing any variable to that? No, it's void. It's just what is the start condition, right? So what I have to do, wherever I, okay, I'll open bracket, then I write here. So this is whichever line you call as SDA, right? What you are supposed to do, SDA should be 1. You see, let's just look at the condition once again, right? You see, initially both SDA and SCL are high, okay, right? SCL, while it remains high, the SDA should be 0, correct? That is my point that I should use to write the starting of my communication. So you see, I initialize SDA is equal to 1, the SCL is also equal to 1, okay, initial condition. Then I'll call a delay function. Anyway, let's write a delay function later. Okay, delay, whatever. Now you enter a delay like 1 millisecond, right? 10 millisecond, whatever you want. So that is what I'm passing here. That is I2C delay. That's my variable which I pass. So it generates certain amount of delay. After certain delay, your SDA should be equal to 0. Correct? 1 to 0 transition. You see, it was 1 initially, it becomes low, right? During which SCL is high. So this is called as uh, the start condition, correct? Then I'll call another delay of the I2C delay. So that stops, right? So this whole process is what we call as the starting condition, right? So similarly, I write the code for stop here. So this is void. I'll call stop I2C. Again, you're not passing any variable to this function. It's void. Okay, open this. Now again, let's go back and check the condition that I need to remember. Both will be low initially, maybe. Okay, you have to make sure that whenever the SDA goes low to high, this should be high. That's all. So you can start with the low condition or you can start with a high condition on SCL. Doesn't matter. Okay, so what I do here, I'll start with both being low. Okay, so SCL is low, right? SDA is also, let's assume that initially it is low, right? Then I call a delay, right? Delay of the I2C delay, that value I'll pass. Okay, it gives a delay of certain amount. We'll write the delay function later. Okay, fine. Now, followed by this, SCL should be high initially, correct? SCL becomes high, you call another delay, delay of I2C, that value, whatever. Okay, I pass that value. Now what should happen? The SDA should be high. It was low here, it becomes high while SCL is 1. So that is the condition should be used using for stop condition, correct? So now that is detected as a stop condition called delay. I2C delay. You can pass any number here, that doesn't matter, so close. So that is what is called as the condition of the stopping. You want to stop means this is how you will do. Okay, is it fine? Okay, now let us look at the write. I want to do a write operation. Okay, so let's look at the write operation now itself. Right. So always remember, the questions can be formed in any fashion, right? So the question could be write a program, write a C program to read the data from EEPROM using I2C. Okay. So if it is read operation, you you have to define the control register initially according to your need, right? Like that, I have to define what is this. There will be a start bit, yes, will be there. There will be control code 1010 followed by the specific address, okay, to which device you want to communicate. Then if they say write a program to read, you make this as 1. Read write bit becomes 1. The write bar says that it has to be 0 if you want to write. Okay, then acknowledgement will come right from the device. Okay, so we'll see right how the operation happens. All right. Okay, now master. So just recall what happens now. Okay, I think I didn't write the side heading. What I'm going to do now. So this is read bytes from the EEPROM. I want to read from this. So how the read operation should happen? Just remember the process. You will be able to write a code by yourself, right? Because right, the operations we already understood. Individual operations we understood, correct? Okay, now we look at right the procedure to be followed for reading operation. First, what happens? Master is the one who decides I want to read. So master puts the start bit on the I2C, right? So start bit we already know now. What is that? We already have written a function. Okay, is it okay? Fine. Then send the control byte to the EEPROM followed by the read. I'm saying that I want to read, right? Then keep checking for the acknowledgement bit, right? Whether the master receives acknowledgement or not, master should keep tracking that, right? So that's the first step. Okay. Now master does not get acknowledgement means what? It will continuously send the control byte again. Now I don't have any other option because right now our intention is just to read something. That's all. Until the device says, yes, I'm here, right? You can do this. You keep on doing this. Okay. So actually there is another part that is called as a, okay, I think before this I will write that because that is very useful. So anyway, in the theory part, we never discussed, but this is going to be happening whenever you don't get the acknowledgement in a single shot, right? You sent a start, whatever this thing, right? You send saying that, okay, I want to start the communication, but none of the devices will reply to that. means you have to do what is called as a repeated start. Okay, there is actually a concept called repeated start, but anyway, when I discussed the theory just before now, I didn't write that, but anyway, I'm going to write a code for that. Okay, so this is called as a repeated. I'll write a code here, okay, directly. So it means not only during the communication, master does not want to release the bus, and it asserts repeated start condition to continue the communication. That is one thing. So that is, this is how it's going to look like. Okay, so it's like void repeated start of I2C, right? You don't have to pass anything, so that will be still void. Okay, now, so what is the initial condition? Initially you start with SCL is equal to 0. Okay, call delay of I2C delay. I call a delay, then I make SDA equal to 1. All right, then call a delay. Now you make SCL as 1. All right, SCL becomes equal to 1. Call delay I2C delay. Okay, once this is done, after immediately after this delay, you make SDA as 0. Okay, SCL becomes 0 to 1. Okay, whenever SCL is 1, SDA becomes 1 to 0. So that is the condition for a repeated start. That this particular operation is called as a repeated start, right? Okay, so then once again you can call a delay. I2C delay is the amount of delay you require and process. Right, so we will be using this repeated delay, right, if required in the during the read and write operation. Okay, so we'll see the read operation as well as write operation, then we'll write the codes required for reading a byte, writing a byte. Okay, so after that, that actually has all the answers required, but we'll write a general program later to do anything you want, like that. Okay, like I may want to do read a byte followed by write a byte, or otherwise I may want to read a byte first, then write a byte to another address and something like that. Okay, so like that, we'll write one general program that is sufficient for you to understand. Yes, okay, this is the whole thing. That gives you a clear picture. Now what we are studying is part by part. Okay, this is how you write, this is how you read, this is how you initialize, this is how you stop, etc. Okay, so that part is over, right? In tomorrow's class, we'll go ahead, look at the writing a byte, reading a byte, then we'll write the whole program, one single program, doing all of them together, which will actually include even the circuit part, right? I'll try to answer one of the questions from your paper itself so that it becomes easy.